From Rolle's theorem, we now have the ability to prove the mean value theorem. So here is the mean value theorem, or MVT for short. We want to be careful not to confuse this with the intermediate value theorem. So if a function is differentiable on the open interval AB and continuous on the closed interval AB, then f of b minus f of a over b minus a equals f prime of c for some c on the open interval AB. So some c that's between a and b. So what does that mean? Well, f of b minus f of a over b minus a. Let's have a look at a function on a graph. Okay, so if I have a very beautiful function here, and I have my point A here, and I have my point B here. F of b minus f of a, so this point up here is b comma f of b, and this point down here is a comma f of a, because f of a is just the y value you get when you plug a into f. So when I draw a nice, and I'm actually not even going to trust my hands, I'm going to use my handy dandy ruler. I'm going to draw a nice straight line between a and b. Okay, then f of b minus f of a over b minus a. So f of b minus f of a over b minus a is the slope of the secant connecting a and b. And it is also the same as the which is the same as the average, and this is where the mean comes from, rate of change of f. So it's the average slope of f over that period of time. So if it were a position graph, it would be the average velocity over that period. So what the mean value theorem is saying is that for some point between a and b, there has to be a point where the tangent line has the same slope. So at this point C, we have a tangent line that is the same or parallel to, with the same slope, our average slope of the function between a and b. Okay, so this sign is line with slope equal f prime of c, which is also equal to average or mean rate of change of f. Okay, so let's look at an example of how this could be used. So basically what this is saying is if you look at the average of the slope of the line, so look at the secant between 2 points, if your function is continuous and differentiable the whole way through, there has to be some point where the slope of the tangent line matches the slope of the secant between a and b, and that point has to lie between a and b. Okay, so let's see an example of how this might be used. Okay. For the function f of x equals 2x cubed plus 3x, find the point c comma f of c in the open interval 0, 3, such that the tangent line at C is parallel, so has the same slope, to the secant line through the endpoints of the closed interval 0, 3. Okay, so given, so we can use these three dots to say given, f of x is a polynomial. Therefore, it is continuous on 0, 3 and differentiable on 0, 3. Remember, if we're defining a function only on an interval, it can't be differentiable at the endpoints. We can't find the derivative at the endpoints. So we can use the mean value theorem. So by the mean value theorem, f of 3 minus f of 0 over 3 minus 0, so the slopes there, are equal to f prime of c for some c. So that means that c has to exist. Okay, there may be more than one c. It doesn't mean there can't be more than one c. So let's actually calculate what that slope is. So we have f of 3, which is 2 times 3 cubed. Let me just check my function. Yep, it is 2x cubed, so 2 times 3 cubed plus 3 times 3 minus 2 times 0 cubed plus 3 times 0. Okay, that over 3, 0. So that is 3 minus 0. So that is equal to f of 3 minus f of 0 over 3 minus 0. So now f prime of c is going to be 6x squared plus 3 evaluated at x equals c. Okay, so we can, this is 3, this is 0, so 2 times 3 cubed, that's just 2 times 3 squared plus 3, so 2 times 9 is 18 plus 3 is 21, is 6x squared plus 3, or 6c squared plus 3. I'm going to evaluate that at c. So 18 is 6c squared, so c squared is 3, and c is going to be equal to radical 3. Why not the square root of 3? Why not the negative square root of 3, you might ask? Well, because negative radical 3 is not on the open interval 0, 3. So we're looking for the c that is on the open interval 0, 3. Negative root 3 is going to be between negative 3 and 0, or it's smaller than 0, can't be in that interval. Okay, so c is equal to 3. We were asked to find the point c comma f of c, so now we have to go and plug the square root of 3 back into our original function. So we have 2 times radical 3 cubed plus 3 times radical 3. So radical 3 squared is 3, so we have 2 times 3 is 6, so we have 6 radical 3 plus 3 radical 3. This is f of c, just to remember what we're finding, f of c. And so this is equal to 9 radical 3. So our point is radical 3 comma 9 radical 3. Okay, so let's have a look at a different kind of example. So if f of 3 equals minus 2 and f prime of x is less than or equal to 4 for all x, okay, what is the largest f of 7 can be? Now this is an interesting problem, and why we would be using the mean value theorem is a little kind of curious. Well, let's see. Okay, so we know that f prime of x, okay, so what are we given? We're given that f prime of x is less than or equal to 4 for all x, okay, So if we know that f prime of x is less than or equal to 4, we know that it is a number, and we know that it is differentiable and continuous. So therefore, f of x is differentiable and continuous for all x. Okay, so we can say by the MVT, we're trying to find f of 7. So we know that f of 7 minus f of 3 over 7 minus 3 has to equal f prime of c. And f prime of c has to be less than or equal to 4. So we know that f of 7 minus f of 3 over 7 minus 3 is less than or equal to 4. So that's the biggest that average value can be, because it has to be equal to a point at some point. So it can't be bigger than any of the values within it. And that's kind of an interesting consequence of the mean value theorem. So f of multiplying both sides by 4, we get f of 7. We know f of 3 is negative 2. Minus negative 2 is less than or equal to 4. So f of 7 is less than or equal to 14. So since f of 7 is less than or equal to 14, this means 14 is the largest possible value of f of x, f of 7.